Okay, so before getting started with the actual lecture today, I don't think I said this on Monday, but because there's an exam next week, there's not going to be homework due that's next week as well. There is homework that's online right now. There's homework 3, but it's due 2 weeks from now. So like the Monday, 2 weeks from now. So really like 12 days. So I would recommend working through the homework before the exam because it is going to cover problems from sections 2.4 to 2.6, which is going to be covered on the exam. But I'm not going to actually collect it until the Monday after the exam. And then, yeah, so the exam next week is going to be on Friday. I plan on making an exam review that I'll be posting sometime either today or tomorrow. And then I think on Monday in class tomorrow, or oh my God, Monday in class, we'll be going over section 2.7, which is where the cutoff for the exam material is. And then on Wednesday, we'll have an exam review day. So I'll spend the entirety of Wednesday reviewing for the exam, which isn't what the syllabus says, but we're going to do it anyways. We're not asleep to the syllabus. Okay, any questions? All this is online on Canvas, like the way the weeks are organized and stuff like this. Any questions? Okay, so where we left off on Monday was we were talking about inverse matrices. And so really we were just focusing on like what are inverse matrices and how do you construct inverse matrices if you're given a matrix A. And we also ended up seeing that not every single matrix is going to have an inverse. So this was an example of starting off with the matrix A and then finding the inverse through this Gauss-Jordan elimination process, which is really just doing the row elimination techniques we've already been using, except there's a couple extra steps. We did a 2x2 example, we did a 3x3 example, and then we looked at an example where the matrix didn't have an inverse. And so a way of determining whether or not a matrix is going to have an inverse or not is you can look and determine whether or not the rows or columns are linear combinations of one another. The 2x2 case, it's a lot easier. You can just see that this row is 2 times this row. That's going to be an indicator that your matrix is not going to be invertible. And so the only other part of this section that's left to be covered is the following theorem. So this is a multi-part theorem, which gives us a lot of useful information about invertible matrices. And so this first part of the theorem is exactly what I just said, or we observed in the previous example. So we're going to have that an m by n matrix is invertible if and only if the Gauss-Jordan elimination leads to n pivots. So what I mean by this is that we're going to start off with a matrix A, and for it to be invertible, and I'll say this is like, we're using row elimination techniques. We need to eventually be able to reduce this matrix to a matrix of the form like A, B, C, all the way to, I don't know, some like VK or something, some number, maybe we'll use like alpha, some arbitrary number where we have that A is not equal to 0, B is not equal to 0, and then alpha is not equal to 0. So this is what I mean by pivots. It's saying that the entries of the diagonal of the row reduced matrix are non-zero. And we'll talk a lot more. I mean, this is something that's going to show up throughout the rest of the semester, especially like when we start talking about row independence and column independence and stuff like that. We'll see a lot more of this. I just want to give an indication of what this language means, really. Like these are the pivots. The pivots are the entries on the diagonal. And so the reason why this is true, or at least the intuition, and again, we'll talk more about this later on, is if we have that there's going to be less than n pivots in the matrix after row reduction, then this is going to tell us the linear combinations of the columns of A are not going to fill up all of Rn. So it's saying like there's some form of dependence between the columns, which means that all n different equations are not going to end up being solvable. And again, we'll talk more about this later on. The second important theorem, or part of this theorem, tells us that the inverse of a matrix is going to be unique. So if we say that 2 matrices B and C are both inverses of A, then we have to be able to conclude that B is equal to C. And so how we can determine this is what the proof of the theorem ends up looking like. So if you have a matrix B that we're saying is the inverse of A, then we can say that B times identity, or B is equal to B times the identity, And if we're saying that C is the inverse of A as well, the identity can be expressed as A times C. And so by the associativity of the matrix product, we can rewrite this product by moving the parentheses into this product. And so if B is also an inverse of A, this is going to be the identity as well. So the BA times C becomes IC, and then that just becomes C because I is the identity. So we ended up showing that B is equal to C. So really, like, the proof of this really isn't so bad. So this shows that you can only have one inverse per matrix, assuming it has an inverse in the first place. This is kind of just like rapid fire. Like, a lot of these statements, they're really useful and the proofs are really quick. So I'm just gonna mention the theorem and then quickly talk about the proof. The next really important part of this theorem is the following. So if we have, I'm assuming this should be n by n. If we have an n by n matrix A that is invertible, then if we have a system of linear equations of the form AX is equal to B, then this is going to end up having a unique solution. And so this is easily seen because if we have AX is equal to B, all we have to do is multiply both sides by A inverse. If we were to do that, we would end up getting that. I don't really like the way this is written. I feel like this is the easier way of writing this out. So if we have AX is equal to B, if we multiply both sides by A inverse, we're going to have A inverse times A times X is equal to A inverse of B. But then the A and the A inverse cancel out with one another. So this is going to end up implying that X is equal to A inverse times B. And because A inverse is unique, there's only one inverse to our matrix, this is going to tell you that the X that we have here is going to be unique as well. So that's how we can determine if A is invertible, and we look at the corresponding system of linear equations, it's going to end up having a unique solution. And then conversely, what the next part of this theorem is going to be telling us is that if we have that AX is equal to 0 has a non-zero solution for X, then X is not going to be invertible. So the idea behind this is if we did have, so if we had something of the form of AX is equal to 0, where we have that this X is non-zero, then we would also have that this A times 0, this is another solution to the system of linear equations. So we have two different solutions. We have AX is equal to 0 and A times 0 is equal to 0. And so this would imply that there's two distinct solutions of AX being equal to 0, which would then contradict the third statement here. Because if A were invertible, this would imply that AX equals 0 would just have a single unique solution. So these two results are related to one another. You use 3 to end up proving 4. And then the last part of this theorem is just going to tell you that if you have two invertible matrices, their product is going to be invertible as well. So if A and B are invertible and you look at the product is invertible, and the inverse of the product is going to have the following form. So we have that AB inverse, so the inverse of the product is going to be the inverse of B multiplied by the inverse of A. So this inverse sign, it flips the order of the multiplication, and then you distribute the -1 to both terms of the product. And so how you can see this ends up being true is you just have to make sure that if you did B inverse times A inverse and you multiplied by AB, you would end up getting the identity matrix. And it's really just a routine check, right? Because if you consider this product, this is the same thing as B inverse and then multiplying by A inverse times A. This is just going to be the identity. So this easily leads to this equality where the A inverse times A becomes this I. And then if we're multiplying by the identity, this product isn't going to change. So it's just going to become B inverse times B, which is equal to the identity. Right, so the A inverse A's cancel out, and then the B inverse B cancels out, and you end up getting the identity. So that's how you'll determine that the inverse of the product ends up being equal to this equation right here. You just multiply them and make sure they end up being the identity. And technically, you have to do it in both ways, but I mean, the proof is the exact same, except you would first multiply B and B inverse and then A and A inverse. So yeah, so these are, I mean, the proofs of these are pretty simple for the most part. I think one would require the most thinking, and it's something we'll talk about later on. But the remaining 4 results, they're really useful and they're pretty intuitive as well, I would say. It all kind of boils down from the fact that, like, if we have a matrix that's invertible, it's almost like it's divisible. Like, you can almost like divide things, which is going to help a lot in determining uniqueness. Okay, so that's all I have to say about invertible matrices, which is section 2.5. Any questions before I move on? Okay, next we're going on to section 2.6. 2.6 is a little bit interesting. I think like the author of the book makes a really big deal out of it. He's like, it's the most important application of Gaussian elimination. I'm like kind of skeptical of that. Like when I first did linear algebra, I didn't really learn about what's going to be called this like LU factorization. So I think it's like useful. It's handy. It gives like a cool interpretation of things, but I don't know. I find this more to be an aside than anything else. So really, this elimination and factorization section, what it's going to allow us to do is we're going to be taking a matrix A, and then we're going to be decomposing it as a product of a lower triangular matrix and an upper triangular matrix. So it sounds somewhat complicated in that wording, but really we're doing the exact same thing we've been doing for the last week. Like we're going to be using elimination matrices to get an upper triangular matrix, and then we're going to use those elimination matrices to get a lower triangular matrix. And then we'll be able to write A as a product of those two things. So it's like doing exactly what we've been doing, except there's one more step at the end, kind of like with invertible matrices. And so they'll be more clear when we actually work through an example. Okay, so what I just said verbally is really just the first 3 bullet points of the slide. So the main focus is going to be factoring a matrix A as a product of a lower triangular matrix L with an upper triangular matrix U. And so this is going to be called LU factorization. And so how this works, and a lot of this is going to be really familiar, despite like this new terminology. So we're going to begin by considering a system of linear equations. So this is a 3x3 system of linear equations on the left-hand side. If we wanted to translate it into the language of matrices and matrix multiplication, it would become the following, where this larger matrix is going to be our A. This 3x1 vector is going to be our X. And then this is going to be equal to this 3x1 vector B. Right, so this linear system of equations is this, really can be expressed as this matrix product, which is this AX is equal to B. And so as we've been doing over the last week, is we want to use elimination to take this matrix A and then turn it into an upper triangular matrix. So all of this is going to be review, like these next couple of steps. So if we started off with this initial matrix, the first thing we would want to do is we would want to eliminate this 2 entry in the 2, 1 entry of our original matrix. So the corresponding elimination matrix is going to be this E2, 1, which is this the identity, except you have a -2 corresponding to this 2 in the 2, 1 entry. And so if you were to multiply this elimination matrix by this original matrix, it would end up equaling this matrix right here. And then you also have to make sure that you multiply your B by the same elimination matrix in order for the equation to be consistent. So after multiplication by this elimination matrix, we end up getting the following system of linear equations. And so a way of rewriting this, and we didn't really look at this perspective before, but really what's going on is we had an equation AX is equal to B, and now we have a new equation of the form of, there should be, instead of E1, it should be E2, 1. But this is like E2, 1 times AX is equal to E2, 1 times B. So we just take this system of linear equations and we multiply by this matrix right here. And then you just keep on going on. So next you would want to get rid of this -1. This would correspond to multiplying by this elimination matrix. After multiplying this matrix that we had before by this matrix E3, 1, you end up getting the following matrix. And so again, what's happening to our system of linear equations is we're multiplying both sides by E3, 1. Yeah, so what happened here is I changed, like the original slide had this as like E1, this is as E2, but I changed it to E21 and E31, and I forgot to change like the right-hand side, unfortunately. But it should be like E31. I'll do it when we get to the end. I'll fix it. And then if we wanted to get rid of the -5, it would be another multiplication by an elimination matrix. This time it would be E32, where we have this 5 here. The reason why it's +5 and not -5 is because we have a -1 entry here and not a 1 entry. So we'll just have to do 5 times row 2 added to row 3. So it'd be a 5 here. Okay, and so what we did is we started off with this equation, ax is equal to b. And really what we were doing is we were multiplying both sides of this equation by these elimination matrices. And of course, like what you do to one side, you have to do to the other. And so where we left off, or where we stopped when we were thinking about this stuff in the previous week, is we'll just use this equation here to then just solve using back substitution. So once you get to this point, you know that 16z is equal to 32. So you'll end up finding that z is equal to 2. Then you plug in like z is equal to 2 into this equation here to determine what y is going to be, and then you plug in what y and z are equal to determine what x is. So like this is kind of where we were stopping before, but writing out the equation in this way gives us some useful insight. So I just want to make sure. Oh yeah, so like this new perspective that we're going to be focusing on today is first we're going to be noticing that through this multiplication that we just did, i.e. multiplying A by these elimination matrices, we ended up getting a matrix that was upper triangular, right? We ended up getting this matrix right here. So maybe I should label to make clear that this is the matrix E32 times E31 times E21 times A. Sorry, I was like super zoomed out, so I'm going to just zoom in. So this is equal to an upper triangular matrix, right? We have 0, 0, 0. So that's kind of where, like, we're talking about LU factorization. So the questions are really like, what's L and what's U? So this is our U. We're halfway done. We just have to determine what our L is going to end up being. And so where the L is going to come in is we have to determine where the lower triangular matrices are. And if you look at the like elimination matrices from the previous example, and really just from the definition of like the elimination matrices, all of those matrices are lower triangular matrices, right? I don't want to give you like too much whiplash zooming up and down, but you can see for E21, these entries are all 0. E31, these entries are all 0. And then E32, all of these entries are 0. So all of these are lower triangular, and that we have like this lower triangle of entries in our matrix that are allowed to be non-zero. And so the elimination matrices are going to determine what the lower triangular matrix is going to end up being. And so the only kind of quirk that's going on is we're not actually considering E21, E31, and E32. Instead, we're going to be considering the inverses of these elimination matrices. And so we're going to be looking at E21 inverse, E31 inverse, and then E32 inverse. And we saw before, this is this review from Monday, if we have an elimination matrix, say like E21 is equal to 1, 0, 0, minus 2, 1, 0, 0, 0, 1, the inverse of this elimination matrix is just going to be taking the entry off of the diagonal that's non-zero and then just flipping the sign, right? So E21 inverse, it's pretty much the exact same thing, except you change the -2 to a +2. So it's really easy to go from an elimination matrix to its inverse. You just flip the sign. So these E21s, like we're still considering E21, E31, and E32 from the previous example. So these are going to be the inverses of these elimination matrices. And the reason why we're considering the inverses of these elimination matrices is the fact that the product of the inverses of these matrices are also going to be lower triangular, right? We just have a product of lower triangular matrices. So if you took the product of them in the order of E21 inverse, E31 inverse, then E32 or E32 inverse, we end up getting the following product. And so if you were to multiply these two matrices together, all that really happens is you're just combining a 2 in the 2-1 entry and then a -1 in the 3-1 entry. And then after you multiply these two matrices together, you multiply their product right here by the remaining matrix, and you end up getting the following. And really the product is just going to be like you're changing the 0 here to a -5 here. Everything else remains the exact same. And so this gives you a lower triangular matrix once more. And so this is what our L is going to end up being. Like L is going to be the product of the inverses of the elimination matrices. The only thing that's a little bit weird is that before, when we were doing the elimination matrices, I hate scrolling like up and down all the time. Initially, we were doing E21, or we were doing from left to right, we were doing E32 times E31 times E21. When considering the inverses, when computing L, we're going to be flipping the order in which we're multiplying the inverses. So we're doing E21 first, and then E31, and then E32. And the reason will be clear here shortly, I think, on the remainder of this slide. Yeah, so the reason why we're flipping the order of the multiplication is that if we have L in the following form, and then U, the upper triangular matrix we had above, so this matrix right here, then it turns out that A is going to be equal to L times U. And it's from this equation right here. And I kind of want to go into a little bit more detail. So I think just writing this out, maybe it looks a little bit strange. But what we were able to determine from before is that we had that E32. Oops. We had E32 times E31 times E21 times A was equal to an upper triangular matrix. It was this upper triangular matrix right here. And so now if you go and you just multiply the left-hand side by whatever, like the inverse of whatever matrix you're looking at, this is going to imply that E31 times E21 times A is equal to E32 inverse times U. And then you just repeat this process as many times as necessary, right? Like you'll multiply both sides by E31 inverse to then get that E21A is going to be equal to E31 inverse, E32 inverse. And then you do the same thing with E21 to end up getting that A is equal to E21 inverse, E31 inverse, E32 inverse times U. And so we saw before that the product of these matrices is lower triangular. It was this matrix right here. So this is going to be our L. So this is telling us that A, oh, I forgot to write the actual L. So this is telling us that A is equal to L times U. So this is where the LU factorization is coming into play, or how you can decompose a matrix A in terms of a product of a lower triangular matrix with an upper triangular matrix. All right, so it all comes down to just finding the elimination matrices, then finding their inverses, and then multiplying them together. If you can do that, you'll be able to decompose your matrix into LU factorization form. So yeah, I think it's like, it sounds like a lot in the beginning, but it's really just doing exactly what we've already been doing, just with another step. Okay, any questions about this whole process so far? Okay, I think all that's really left. Oh, I think there's like a remark that needs to be made, and then we'll do an example. Okay. So where this like LU factorization, and just like any other process we've seen so far in this class, is there's going to be parts or certain matrices where this doesn't really play well, or it's hard to do this LU factorization. And like usual, the difficulty is going to occur when we have zeros where we have pivots. So if there's like zeros on the diagonal, there's going to be issues. And the reason why it's going to be problematic for like doing this LU factorization is that the permutations that we were looking at, like the permutation matrices we were looking at before, where you switch certain rows of like the identity matrix. So these are examples of 3x3 permutation matrices. You can notice that none of these matrices are going to be lower triangular. So if you get to a certain step in the process of reducing to the upper triangular matrix, and you end up getting a 0 in the pivot, you can't really multiply by a permutation matrix, because then you're not going to have a lower triangular matrix as your product anymore. So what this means that you have to do is that before you even go through with this LU decomposition, you have to begin by multiplying by a permutation matrix. So that's what this final statement is saying right here. If we end up having a 0 in the pivot, we can permute the rows of A using a permutation matrix and then perform LU decomposition. So really, you're performing LU decomposition on the matrix P times A and not A itself. So that's going to be an issue. And we'll see an example of this, not in the next example, but in section 2.7, we'll work through an example where you have to use permutation matrices and then apply the LU decomposition. So it's really just something to keep in mind. And then the important, like one of the important applications of this LU factorization is the following. So, oh yeah, I felt like this is like he was putting a lot of emphasis on this fact. So like what we've been doing before is we've been using elimination to lead to solutions of the form like of the equation AX is equal to B for one vector B. And then he says like the LU factorization can be used to solve AX is equal to B. But I don't really see like how much more insight the LU decomposition really gives in finding solutions to this equation. Because like what he's saying is that if we have AX is equal to B, if we have an LU factorization of A, this is the same thing as saying that L times U times X is equal to B. And so if we wanted to solve this equation, it's the same as just doing U is equal to L inverse of B, or L inverse times B. Because we know that L, it's a product of invertible matrices, so L is going to be invertible as well. So this means that you would have an upper triangular matrix times this product right here. So then you can use back substitution from here to solve your system of equations. I guess like why I'm skeptical about why it's like such a big deal is we kind of already, like to get this LU factorization in the first place, we kind of already determined what like the upper triangular matrix is, and then we can just solve from there. But I think there's applications in programming that where like LU factorization is preferable to just doing like row substitution, I suppose. Okay, so I just wanted to go through one example, and then this will finish section 2.6, and then we'll go on to section 2.7. So for this example, it wants you to find the LU factorization of the following matrix. So this is just going to be a 3x3 matrix A. And so really the first half of this is going to be finding U. The first thing we're going to do is just find U. And then once you determine what U is going to be, that's going to allow us to determine what L is going to be. So the first step is going to be finding U, which is something we've been doing for, I think, like a week at this point. It's taking a matrix and then reducing it to an upper triangular matrix. And because we're doing LU factorization, we're going to want to think in terms of elimination matrices and not the row operations. So I'll go through this because this first step is pretty familiar. So I'm going to go through this relatively quickly. So if we want to get rid of this 3 right here, we'll take row 2 and subtract from it 3 times row 1. So the matrix is going to be 1, 0, 0, minus 3, 1, 0, and then 0, 0, 1. We then multiply it by 1, 3, 1, 3, 7, minus 2, 2, 4, 2. First row stays the exact same. Only row that changes is the second. So this is going to be 0. You have 3, or you have minus 9 plus 7 is going to be minus 2. And then you have minus 3 plus minus 2 is equal to minus 5. And then the third row stays the exact same. And if I make any mistakes with matrix multiplication, feel free to point it out. I'm finding it's like hard to do matrix multiplication, like when you're teaching class or like doing it in front of other people. I don't know why. Okay, next we would want to get rid of the 2 here. So the elimination matrix is going to be the identity matrix, except now we have a minus 2 in the 3, 1 entry because we're going to be taking row 3 and subtracting 2 times row 1. Then we multiply by the matrix we had on the equality on the right-hand side. If we multiply things out, the first 2 rows stay the exact same. We're not doing anything with them. The 3 of 1 entry is going to become 0. Then we have minus 6 plus 4 is going to be equal to minus 2. And then we have minus 2 plus 2 is going to be equal to 0. Let's see. Am I correct so far? Oh, okay. I see what ends up happening. Let me make sure. I'm pretty sure this should be correct. Okay, I just wanted to make sure. Yeah, and so then the last step, I got really paranoid seeing the 0 here, but then you have to get rid of the minus 2 and then like it'll become non-zero here. Okay, and then the last thing we want to do is we want to get rid of this minus 2. So what we're going to do is we're going to take row 3 and subtract from it row 2. That's going to be 1, 0, 0, 0, 1, 0, 0, minus 1, 0. And if you multiply, oh yeah, there should be a 1. And this will be 0, minus 2, minus 5. This will be 0. And then you'll do minus 2, minus 2, plus minus 2 will give you 0. And then you have just 5. Oh, sorry. Yeah, I feel like my brain doesn't work in the morning. Yes, this is what I was multiplying this matrix by this elimination matrix, and it ends up being the following. Okay, any questions about how I got this matrix? Okay, so this is U. This is how you determine what your U is. It should be a pretty familiar process at this point. And so to determine what your L is going to be, is you just take each of these matrices. So this is E21. This is E31. And then this is E32. And then we have that L. Is this going to be the product of these, the inverses of these matrices? So L is going to be E21 inverse times E31 inverse times E32 inverse. Where all you do, again, to determine the inverses of these matrices, so the inverse of E21, it's just going to be E21 again, except you flip the sign of the minus 3. So it's going to become 1, 0, 0, 3, 1, 0, 0, 0, 1. E31 inverse is just E31 again, except the minus 2 becomes a plus 2. So this will be 1, 0, 0, 0, 1, 0, 2, 0, 1. And then E32 inverse is just the same as E32. You just flip the minus 1 into a positive 1. So it'll be 1, 0, 0, 0, 1, 0, and then 0, 1, 1. And if you were to multiply these matrices together, you would end up getting the following. So it's going to be a lower triangular matrix of the following form. So this is what your L is going to end up being. And so then through this process, we determine that our, let me label this, this is our L. So we determined that this A is being equal, like this is equal to L times U, where L is this matrix, and U is this matrix. And if you really want to check, you can multiply these two matrices together and make sure that it ends up actually being equal to the matrix A that we originally had. Okay, any questions about finding? Yeah. So we're not trying to get it like identity regions, we're just trying to get it in upper triangle form. Yeah, so getting to U is just like getting to the identity, except we don't worry about getting rid of the -5, 1, and 3. Yeah, really just like reducing to the identity matrix. At least this point in the semester, it's only used if you want to find an inverse matrix. Here we're kind of concerned with just focusing on like solving a system of linear equations. If you're just focusing on solving a system of linear equations, you usually just reduce to upper triangular form and then use back substitution. Okay, any questions about this example? Okay, and again, like really the only new part is just multiplying these invertible matrices or inverse matrices to get what L is. That's really the only new thing that's happening here. So it's not too heavy. Okay, so I think 2.6 feels like more of an aside to me. There'll be 2 problems on the homework regarding section 2.6, and they're pretty much just the example we just did. I'll be asking you to find the LU factorization of 2 matrices. One of them is just like a little bit weird, so it makes it interesting. Okay, so this is the last section from chapter 2. So it's focusing on transposes and permutations. This stuff is pretty important. Transposes show up throughout the rest of this semester. It's like one of the most useful tools in linear algebra. So it's worth spending a decent amount of time talking about it, or at least an entire section talking about it. The idea is pretty simple though for transposes. And we'll see that a lot of the properties of transposes are pretty nice as well. So just going into the definition of a transpose is we're going to be assuming we have an M by N matrix A. And so what the transpose is going to do is it's going to create an N by M matrix denoted by this A superscript T. So this is going to be A transpose. And so all you have to really know about the transpose is that the entries of the transpose matrix are really just going to be the entries of A, where you swap the rows and the columns. So the IJ entry of the transpose is the JI entry of the original matrix. So maybe written like this, it looks a little bit weird, but once we go through an example, it'll be clear, and you'll all like the transpose. And this should be an M, not an N. I'm using slides from someone from a previous semester, and I don't catch every typo. As you've noticed, there's like a decent number of typos. Okay, so really, I think the simplest way of thinking about this is that if you're taking a matrix, so ignoring this T right here, our original matrix is this A. So this is a 2x3 matrix. And after applying the transpose, it becomes a 3x2 matrix. And all we're doing with the transpose is that we're making it so that the rows of our matrix become the columns of our matrix. I think that's the easiest way of thinking about things. So the first row of our matrix becomes the first column of our matrix, and then the second row of our matrix becomes the second column of the transpose. Another way of looking at this again is this is the 2-1 entry of our original matrix. This is the 2-1 entry. It then becomes the 1-2 entry in the transpose. So all we're doing is just flipping the order of the indices. We're just doing a switcheroo, I guess. And then you do, so this is like a rectangular matrix, 2 to 3, 3 to 2. If you apply to a square matrix, it's again going to be a square matrix. you just change the number of rows to the number of columns and vice versa. It's still going to be a 2x2 matrix. So you can see the transpose is going to fix the diagonal of the matrix. So the 3, 2 becomes 3, 2 again. This should make sense because we're really just taking the 1, 1 entry. If you switch 1 and 1, you get 1 and 1. So it becomes the 1, 1 entry again. Same with like the 2, 2 entry. This becomes a 2, 2. The only thing that changes are the terms on the off diagonal. So 2, 1 becomes 1, 2. And then 1, 2 becomes 2, 1. And then again, you can think this is the first row, becomes the first column. Second row becomes second column. There's a lot of different ways of thinking about it that are correct. Okay, any questions about like the definition of the transpose or what we're doing with it? Okay. And so next, like we're just going to be going into properties of the transpose. There isn't anything like super groundbreaking about the transpose yet, but it'll show up later in the class in terms of like how it's going to be useful. Right now, we're just recording properties of the transpose. So what we've seen so far in this class, if you take a matrix A and you multiply it by a vector X, you can represent the product as being a linear combination of the column vectors of our original matrix A with the xi components of the vector serving as the weights of the linear combination. This is something from, I think, like the first week of class, or it's like from chapter 1. It's like matrix multiplication can be viewed as a linear combination of column vectors. And so something that's interesting is that if we were to consider the transpose of X multiplied by the transpose of A, we would end up getting the following product. So this is just the definition. The transpose of X would now be a 1 by n matrix. And then A transpose is still going to be an n by n matrix, except now the first row is the first column. So this is A transpose right here. And so what ends up happening is if you multiply these two matrices together, you would end up seeing that this product can be represented as a linear combination of the rows of A with weights x1 to xn. And you can also tell that these vectors are the same as one another, except they're just flipped. So this is a n by 1 vector, and this is a 1 by n vector, and their entries are the exact same as one another. So if you consider the sum of these matrices and the sum of these matrices, you would end up getting the exact same matrix over again. So what this is saying is that like this AX ends up being equal to AX transposed times A transposed. And so the key observations from the previous slide are that the rows of A transpose are the columns of A. There's something I kind of noted already. And then we also have that the transpose of A times X is equal to the transpose of X times the transpose of A. And this is something that's going to hold in greater generality. Like really, we're just considering the case where we're multiplying a matrix A by a vector. So the natural question would be, what happens if you multiply two matrices together and then looked at their transpose? So that's what this next proposition is going to be asking about. And in general, this isn't really a proof-based class. I'm not going to ask you to do a lot of proofs on like quizzes, homeworks, or exams, but I feel like it's good to prove things every now and then, especially if you want to make use of it later on. So how the proof of this would look like is we're going to assume that A is an n by P matrix, and then we're going to assume that B is a P by M matrix. Let me write it just like this. And so we just want to see what happens to the entries of the transpose and see how they can end up being equal to B transpose times A transpose. So the ijth entry of the transpose of A times B is really going to be equal to the jith entry of A times B. And so by definition, matrix multiplication is really just going to be looking at a dot product of like rows of A with columns of B. So you can express this as being equal to the following sum. The sum has been written out in the past, but it hasn't really been seen too often. So you can write out the sum in the following form. So this is going to be A JK times B KI. So this is really how you would represent that the jth entry is going to be the dot product of the jth row of A times like the ith column of B. And so you can do something clever here. And you can note that this is going to really be equal. So I'm writing this sum out some more. This is really equal to like the transpose entry Kj of our matrix. And then this is going to be times the transpose of B, except the entries are going to be Ik. Like if we're doing the matrix, it would flip the order in which this is going to be considered. And then because these are ultimately, like we're looking at the kjth entry of the transpose, like this is going to be a real number, and this is a real number as well. So you can switch the order of this multiplication. Like again, these aren't like we're looking at entries of the matrix, not like the entire matrix in itself. You can't switch the order of multiplication generally, but if you're looking at like the kjth entry and the ikth entry, you can switch the order. And so this can be expressed as the sum from k is equal to 1 to p of the ikth entry of the transpose of B times the kjth entry of the transpose of A. And then by definition, this is just equal to the ijth entry of the transpose of B times the transpose of A. So this is really equal to B transpose of A, or the transpose of B times the transpose of A. And this will be the ijth entry, or it's like the I and the J here. So maybe this is, again, I'm not going to ask you to do stuff like this on like the exam or anything like that. And I understand it's kind of like a jump in difficulty, but this is how you would see that the transpose of A and B ends up being equal to the product of the transpose of B times the transpose of A. Any questions about the proof of this proposition? Okay, yeah, I think this is a fine place to stop. And it's like written out in more detail here, I suppose. But it's pretty much exactly what I just wrote down. Okay, so we'll stop there. I'm gonna stop recording. I also have your quiz 2 and your homework 1 from the previous week.